Hello, and thanks for listening to me. Today I'm going to tell you about the minimal volume hyperbolic three-orbital fold that has one rigid and one non-rigid cusp. So I'll mention what these terms mean shortly. First off, what's a hyperbolic three-orbital fold? Well, we can just think of it as a quotient of hyperbolic three space by a discrete subgroup of its isometries. And throughout this talk, we'll just think about working in the upper half space model of H3, which we can just think of as the set of points above the XY plane in three space. And with an appropriate metric, this set gives us a model for hyperbolic space. And in this model, geodesics are either vertical half lines or Euclidean semicircles perpendicular to this plane at the boundary of H3, which the boundary is really think of as the sphere at infinity given here. So let me give you an example of one of these orbifolds. So consider this pyramid in H3 with two ideal vertices, one at infinity and one at this point 1/2 plus I root 3 over 2 in the plane. And let's let gamma be the group of isometries generated by, if you take the rotation with the order given by the label on an edge, the rotations about the edges of this polyhedron, and take that group of isometries. And if we quotient H3 by that group, well, we get an orbifold, and a fundamental domain for this orbifold is two copies of this pyramid, it and one of its images under one of the rotations. And you can compute its volume is 5/6 times the volume of a regular ideal tetrahedron in H3. So we're going to obtain lower bounds on the volume of an orbifold by obtaining bounds on the volumes of its cusps. Now, what's a cusp? For us, we'll just think of it as a subset of the orbifold, which lifts to a disjoint set of horoballs in H3. Now, again, in the upper half space model, a horoball we'll think of as being centered at some point on the sphere at infinity. And so if it's centered at a point in the complex plane, that horoball is just a Euclidean ball tangent to the plane at that point. And when I talk about the radius of a horoball, I mean the radius of that Euclidean ball. And alternatively, if for a horoball centered at infinity, the horoball is just the set of all points whose z coordinate is greater than or equal to some fixed value. So looking back here, our orbifold has two cusps, a non-rigid 2-2-2 cusp and a rigid 6-3-2 cusp. Now these labels just tell you when you take a cross section of the cusp, you get a Euclidean 2 orbifold. And so the labelings tell you what Euclidean 2 orbifold you get. So let's place a horoball centered at infinity and let that cover the non-rigid cusp. And let's place a horoball at the other ideal point of our pyramid of radius 1/2 and let that cover the rigid cusp. And now if we apply the isometries in gamma and translate those horoballs around, we can generate this picture on the left where what we're doing is with our eye at infinity, from the perspective of we're inside the non-rigid cusp looking down on the plane, we see this circle packing. Likewise, we can change perspective so that our eye is inside the rigid cusp looking down from infinity, and we get this circle packing. Now, a sphere packing result of Baratsky implies that the volume of the orbifold is bounded below by a multiple of the volumes of its disjoint cusp neighborhoods. Now, in this example above, where we have the two cusp neighborhoods, which give us horoball packings like these, this bound is actually sharp. So this right-hand side is 5 V0 over 6. You might guess that from the fact that these circle packings we see here are the densest possible in the plane. Now, our result is that O, this orbifold we've been talking about, has minimal volume over all hyperbolic 3 orbifolds with one rigid and one non-rigid cusp. Now, how do we go about proving this? Well, it naturally breaks down into cases, depending on how the two cusps interact and where the full-sized horoballs are located in the cusp diagram. So each possible case based on these two possibilities gives us some partial data for the horoball packings. And now in each case, we'll either try to show that the volume of the cusp is large, or we can actually find some volume that is in the compact part of the orbifold to get an appropriate lower volume bound. Of course, in that situation, we're going back to the lower bound that follows from Brodsky's theorem. So here's just sort of a cartoon example of what I mean in each case. Let's say that these red horoballs are your full-sized horoballs, and here you have another horoball of a fairly large size, okay, in terms of its radius. Now, to accommodate this horoball, because these horoballs and their translates, they can't overlap, the area of the cusp needs to expand, and larger area in the cusp means also a larger cusp volume. Now, what about in this case B? So, this is where we're going to find extra volume in the compact part. So maybe we have here our full-sized horoballs, and this is looking down from with our eye at infinity. But if we look, say, from the side, we see something like this. Now, if this little blue one happens to be sort of the largest, next largest horoball compared to these guys, well, there's going to be some volume that we can find in this region here that's going to project down to the orbifold, and we can get a volume bound that way. And I believe I'm probably out of time to go into any further details, but that gives you some flavor of how this argument goes. Thanks for your time.